Hope everyone is having a great MPLS World Congress 2024. My name is Guion Mishra. I am an IT technologist and innovation specialist with Verizon, and today I'll be showcasing groundbreaking innovation R&D work with segment routing, SRv6 microSID in the data center space. This is a demo 9 of 9 video. At the bottom you can see highlighted, this is the 9 of 9 video on SRv6 microSID end-to-end. All of the videos are housed on the YouTube channel at the top, and then all the configs and research and development work is stored in the segment routing SRv6 Labs GitHub and in the subdirectory in red. The goal of this presentation is on the topology. It's a multi-pod, multi-domain fabric. We'll be doing 3 different types of host attachments that we'll go over: Linux kernel, VPP, vector packet processing, and then router in a container. The real good world use case we will be going over today is SRv6 uSID end-to-end. So here the fabric is feature rich, so traffic engineering, all carrier grade features are a requirement for feature richness in the data center, and then steering is initiated at the data center host attachment, and or could be done at on any switch within the fabric. So the goal of this presentation that I gave at MPLS World Congress, as well as here, is really how SRv6 microSID being able to leverage that vanilla IP data plane, and we're able to break down the barriers of solid networking and issues that exist with legacy technologies that we have today with IPv4 transport and our MPLS transport. You overcome all of that with SRv6 microSID, which translates into ultra-massive scale, end-to-end interdomain routing, and being able to leverage that vanilla IP data plane for seamless stitching end-to-end. So with SRv6 microSID, the real big power and the sheer power behind the SRv6 microSID is really breaking down those barriers between domains and as well as subdomains within the domain. So instead of having specialized commodity hardware NVO encapsulations or MPLS encapsulations, now you have uSID. You have an IP data plane, so the IP data plane can stitch your fabric end-to-end. So whether it's IP or SRv6 microSID, since we're steering with the uSID carrier destination address, you can seamlessly stitch and integrate end-to-end across the domain, whether it's an OAD, one administrator domain, or even the internet. Throughout our research and development work with SRv6 microSID, there's 2 key points that came up, and one is in order to do SRv6 across interdomain boundaries where you have inter-AS peering, on your inter-AS peering you have to do next hop unchanged, and then on your IBGP peerings you have to do no next hop self. So traditionally on your P to route reflector peering, you generally have a next hop self rewrite to the loopback. So when that rewrite happens, either in the IBGP no next hop self, or eBGP where you do a next, or where you are the next hop is changing. What happens is when the label changes and the next hop changes, the service SID changes. Since the service SID is the label, and when that changes, the data plane is broken. So this preserves. So the goal is really preserving that SID. So the SID is on each PE or SRv6 microSID capable device, and it advertises that SID. So that SID needs to be preserved on the interdomain boundary. So once if that rewrite happens or next hop change happens, that breaks the data plane because now the SID changes and it's not able to get propagated, and now you don't have that contiguous data plane across that interdomain boundary. The other big key is locator reachability. That's it. I mean, it's that simple as that. Routing simplicity. As long as your summary locator, as long as prefix match are advertised between the domain boundaries, you have full reachability and you can build that data plane. One key point that came up through our development work is a knob that was required on interdomain boundaries where you have SRv6 microSID in order to build that inter-AS peering, is that the route, the next hop, becomes inaccessible. In order to get around that, there's a special knob to get around that, and it's ignore connected check. And it goes right on the peer and applies to all the affy-saffys that are nailed up onto that peer. So with SRv6 microSID design, there's the top-down and bottom-up, and a lot of this I've gone through in the MPLS World Congress, and this is just a kind of recap, real quick highlight. But there's the highly complex data center or fabric, and then there's a vanilla. They both have their use cases, tremendous use case in either case. In this slide deck, where we're going to be doing the highly complex. So we're at SRv6 end-to-end, and in this case, the requirement is highly complex. We need all the bells and whistles, full feature-rich SRv6 microSID and all the segment routing features. SRv6 host-based networking. So there's 4 host-based networking types. There's eBPF Cilium, native Linux kernel, FDIO VPP, and router and a container. I will be focusing on the 3, and we'll be doing end-to-end use cases on. The first one is eBPF Cilium. So eBPF Cilium, the beauty behind eBPF Cilium, why it's the option number 1 for service providers, is that it is one of the most popular CNIs in the native cloud native landscape today with Kubernetes. Cilium is really the most popular one, so you don't need no added software, additional software. And then eBPF has been used, has its origins in the Linux kernel, where it's used to bypass the Linux kernel for adding new features and enhancements to the kernel versus waiting long time cycles to get features into the kernel. So it's been around already for a long time, eBPF. And with CNI, it really is the number 1 top choice for host attachment. Native Linux kernel. So this native Linux kernel is number 2 most desirable for host attachment. And with that, the native Linux kernel has supported programming the fib entries into the data plane natively since 2022. So it provides the data plane programming. We need an open BGP, FR BGP for the control plane BGP advertisement. And then there's options of programming the fib entries. Either FR can program the control plane via Linux kernel call to program the fib entries, or alternatively, FR can program the control plane, which can hook back to the Linux kernel and program the data plane fib entries. FDIO VPP. So this FDIO VPP is the 3rd desired option for host attachment types, and that is because it does require a separate piece of software. So with FDIO VPP, it's able to program the data plane. It requires FR BGP for the control plane advertisement. It sees the control the Linux host NIC. And then it programs the VPP fib entries, requiring a separate component netlink to program the fib entries. And vector packet processing is there for high performance network stack, supports high bandwidth CPU intensive applications. The last one is a router and a container. So router and a container, XRD, Sonic, most vendors support a router and a container today. And router and container, you could think of it as like a CNF, basically container network function overlay. So it requires a Linux bridge to the Linux kernel, and then it runs in user space. However, because the CNF router and a container network function, you can have virtually an infinite number of interfaces. There's no limit to the number of interfaces, so it can support n-app workloads. So this slide shows, and this was in the MPLS World Congress review that I gave today, of the control plane and data plane. So just a quick recap on that. So basically the data plane for eBPF Cilium, the data plane path it bypasses the Linux kernel, and the eBPF has direct access to NIC to the outside world. And then Cilium provides a control plane. Linux kernel, basically your Linux kernel is basically programming the fib entries directly, native support for SRv6 microSID, and then it provides a data plane functionality, and then you require FRR for the control plane. FDIO VPP, so here FDIO VPP requires netlink to program the fib entries for the data plane, and VPP sees the NIC, and then it has full control of the NIC, and then it provides that data plane programming for SRv6 microSID. And then for the control plane, it requires a separate open BGP, FR BGP for the control plane. And last is router and a container, provides control plane and data plane. So it has a BGP control plane peering to the route reflector external, and then it has the for the control plane, it builds, and for the data plane, it's able to program the Linux kernel, and it seizes the NIC, and then it builds the data plane path for steering. So today in this use case, we're going to be doing SRv6 end to end. So from ingress all the way to egress, a full feature rich. So in this drawing, what I have here, we have at the bottom here, we have multi-pod, and then we have core. We have 3 domains in the core, and then at the top here we have multi-pod as well. At the top, this is actually a single IGP area, single AS. It's ISIS level 2 at the super spine, and then at the border leafs we have level 1, level 2 border routers, and then the leafs layer is level 1, and the spine layer, leaf and spine layer are level 1, and then and at the top, the host attachments, we have Linux kernel for the host attachment at the top here, and this is in Berlin. And then in gold, we have router in a container with the app application, like could be a Kubernetes or container networking workload that hangs off of the router in a container. And that's the gold, and then the brown at the very top there. At the bottom here, we have a dual pods. So each pod is a separate BGP-AS, pod 1 and pod 2, and then they connect into the core. So as I had spoken before, I guess all of this is wherever there's an eBGP peering, we have that ignore connected check knob on XRD. So all of this is built using XRD virtualized environment. So in the interdomain boundaries, you have that ignore connected check, and then of course you have the next hop and change on all the eBGP ties, as well as on the iBGP you have no next hop self. So just native, so that you preserve the uSID on the interdomain boundaries, as well as on the iBGP PE to power reflector peering. So in this demo, we'll be going through we'll be going over VPP, and this is a uSID carrier. And what we'll do is we're going to take a peek at, we're going to start a ping stream. This is going to be doing global table routing, and we're going to be steering traffic, the traffic stream, and we're going to take a peek on router 4 and see the uSID carrier set, and see that shifting forward happening. Next, we'll be doing Linux kernel. So that'll be the next host attachment use case. And so the Linux kernel uses IP route 2 for the programming the data plane. And there as well, we're gonna take a peek on one of the nodes along the hop, and we'll see the data plane being programmed, and we'll see the capture of the uSID carrier and the shifting forward happening along the path. So on the GitHub, as I mentioned, we have all the configs they're all uploaded, and they're on the GitHub from all 9 videos. This is the 9 of 9, and in there, in the configs, we have some feature-rich, nice features that we've added throughout the topology. So we have UPA. So some of the more popular SRv6 microsyd features. So you got UPA for BGP pick trigger. You got SR policy ODN with the different locators, candidate paths. With weights, you're doing UCMP, static ERO, dynamic ERO, and stateful. So in this lab setup, we'll actually do a demo of the UCMP doing end-to-end steering. We have TILFA and microloop avoidance. We got SRPM on all nodes, including the host attachment. And then as well, we got PCE, path computation element, on all nodes, including the router and container. In our demo that we'll be doing, it's static SIDless, so we won't be using PCE for the router and container scenario. So now, right, so now what we're going to do is we're going to look at VPP first. So With VPP, we can take a look at the policy. So there's that's the uSID carrier right there. uSID carrier is programmed, and then we have a uSID carrier for V4, and then a uSID carrier program for V6. And in this setup, what we're going to do is we're going to just look at the steering with SRv6, and then here's the steering policy. So that's programmed with the VSID. So what we'll be looking at is this. We're going to do a continuous ping. So on the global table, so the data center fabric being attached to the host fabric and providing that end-to-end steering interdomain. All right, so now what we're going to do is we're going to hop on one of the nodes, and we'll look at this. So what we're going to do is we're going to look at between router 4 and router 2. So right here we're going to do a capture on this link. So we're actually down here in the path. So we're on this node right here, VPP, and we're steering up through the core, and then we're going to take a capture here, and we'll see the uSID carrier set. So we're going to take a look at that. There you go. So there you can see the uSID carrier being set. See that it's node 4, so we haven't got node 4. So this is the link between 2 and 4. So as soon as it gets past 4, then you would see the shift in forward happen. So now what we'll do is we'll take a look at on the between the next link up. So that would be off of router 4. So, and then we can see the, we'll just see that hop. So let's say we go between router 4 and router 8. There you go. So now you saw the shift in forward happen. So see that's the 4. So we went past router 4, we were going between router 4 and 8. So we did the 16-bit shift in forward. So now we see 64 and 66 in the left in the uSID carrier. So next, what we're going to do is we're going to look at VP. We're going to look at Linux kernel. All right, so Linux kernel, we have the uSID carrier is set right there, and we're going to start a continuous ping. And we're going to do the same capture. So we're also still looking at the link between router 2 and router 4. So let me see. So we're looking between you see between router 2 and router 4. Just give me 1 second. Let me start the ping again. All right. What we'll do is we'll look at between router 64 and 61 actually to start. So let's say we do router 64 to router 61. And for some reason, we're actually not seeing the uSID carrier set. But what we'll do is we'll pick this up in a future video. This part of the demo today. We're gonna move on to the next demo, which is really the big one, the looking at router in a container, and that's doing end-to-end SRv6 microSID. So this last video, what we're going to do, with this last step of the video today, we're going to take a look at the router in a container. So what we're looking at here, actually I'll just show the video. So we're going to be on this router here, router 87. So he's connected to router 46, and he is basically a container network function. He's doing the control plane and data plane. So this is similar to any host where you have an app, like it could be a Kubernetes app or many apps that are actually being front-ended by this. They're connected to an interface off the container router in a container, and then he's doing that CNF function, programming the control plane and data plane. It has a BGP peer upstream northbound, and then it's programming that data plane end-to-end path. So that's exactly what we're going to look at right now. So what we're going to do is we're going to have two paths that we're going to look at. We're going to be looking at a trace. One is going across our algo 0, so algo 0 topology, and then the second trace. And what's going to happen is in this trace we're doing multipath. So it's doing multipath load balancing with a candidate path with two different weights. So the one that we are doing the policy is this one right here. This is the first one we're going to be looking at. So it's got a weight of 2 and 4. So what that is, it's basically 2/6, so 1/3 and 2/3. So 1/3 of the traffic would go across the first segment list, and then 2/3 would go across the second segment list. And we're going to do that right now. So with that one, there's two SID lists for that. So the first SID list is here, and then the second SID list is this one right here. So there's two SID lists. So they're going 46 to 44, and then 47 to 44 on the SID list. So the route that we're going to be looking at is Actually, before we look at the, we can look at the policy. So this is the path. So that's the SR policy that we're going to be looking at right now. So here's the route. You see, it's got a color 3000. So that's the route that we're going to look at. So that candidate path, so it's bound to the forwarding plane. So we get a color, so the color signal from the egress PE to the ingress, color 3000, and then that's that signal to the SR policy with that same color, and then the candidate path is bound to the forwarding plane. So here's the SR policy. It's tied to the color 3000 on the VPN, and then that provides the VPN overlay prefix to underlay path instantiation of the steered path. So there's 3 flows that we're going to be looking at, and we're going to be doing a multi-path. So we have two SID lists tied to a candidate path that's bound to the binding SID. And here's the binding SID here. That's the binding SID for the candidate path. So we have that route, and then we have this one here. This is the second flow. And then the third flow is yeah, 35 to 28. So it's this one right here is the third flow. Okay, so those are the 3 flows that we're going to be looking at, and we can see that the two lines to actually look at is we have this. That's that's the next hop. Look back. We have the color. We have the binding SID, and then you have the next hop. So that's the reflector that the path we received from, and then you have the SR policy. The candidate path is bound to the forwarding plane, and you got the coloring for the SR policy, and then the BSID for the candidate path. So now what we're going to do is we're going to start up stream. Right, and then now what we're going to do is we're going to do a capture. So what we're going to do is on the capture, we're going to look at the path. So we have it. This is a UCMP scenario. So unequal cross load balancing. We're doing 1/3 and 2/3 across the 2 paths. These are the 2 segment lists. So what we're going to do is we're going to do a trace between 46 and 44, and then 47 and 42, and to see the UCMP traffic. Alright, so that was between 46 and 44, and you can see this is the USID carrier being set. You can see the hops, so node 44, then node 7, 64, so you see the whole path being set. So now the next trace we're going to do is the other path, and that is going to hop between router 47 and 42. And you can see the uSID carrier being set there as well. There it is right here. So you can see the uSID carrier. There you go, being set. So this concludes the demo for SRv6 microSID. Hope everyone enjoyed the demo, and stay tuned for future research and development work done. And as you know, as future work is developed, I'll be posting that up on the YouTube channel, as well as posting updated configs. Thank you very much, and have a good day. Thank you.